Yeah. So this is the theorem that we stopped with. Let me go back to the page where I had this. So the theorem claims that there is a lambda algebra homomorphism from our cuspidal Hecke algebra T to a lambda algebra W, which has a very explicit description. So it's a power series ring, polynomial ring in R plus 1 variables over E mod out by this ideal. Okay, so there are these relations, pi to the R n plus 1, epsilon I squared, epsilon I times pi, and the product, this is the most important relation, product of all the epsilon i's is the analytical invariant to pi to the R n. So more or less that thing. Okay, and we know what how this map behaves on there's explicit Hecke operators that we have, TL and so on. So it sends TL to 1 plus chi times epsilon L. So this epsilon is the lambda-adic cyclotomic character. It sends these operators UL to 1 for all n which are not above these primes in R, which are not the primes in R1. And it does something interesting at primes in R1. So it sends this UP operator to 1 plus epsilon R. Okay. And I calculated for you the the action of these UP operators on F tilde yesterday. So I'll not do that again, but let me sketch the proof, sort of the ideas how it works. So as well as introduce some notation. So lambda sub 1, this is the space that we are working with. Okay, so we are working at weight 1, so we don't really care about other weights. So I'm localizing my lambda at weight 1, which means that I'm inverting everything which is outside kernel of this map V1. Okay, there's this map, right? This thing V1 from lambda to E. Okay. All right. So okay. S0. So remember, without this O at the top, this was the lambda-adic space of cusp form, and this O at the top just means the ordinary part of it. So so if you like, this is E times S n chi. Okay. So that's what the Hida operator gives you, the ordinary part of the space of cusp forms. And then I localize that at weight 1. So I'm only concentrating around my weight 1 points. Okay. So there's a map from this ordinary cusp forms to product of all the lambda 1s, and these are indexed by non-zero ideals in OF. Okay, what the map is a simple one. It just takes any cusp form and sends it to its Fourier coefficients. Okay, normalized Fourier coefficient. So that's what the map does. It's a simple map. But this is precisely the map that gives us this theorem. Okay, and so now this space is all cusp forms. I don't want to concentrate on all cusp forms. I only want to concentrate on cusp forms which lie in the Hecke orbit of my F. Remember, last time I said F will almost surely not be a eigenform. In general, most of the times it will not be an eigenform. Whereas if I want Galba representations, if I want to relate it to arithmetic theory in a nice way, I want Hecke eigenforms. So what you do, instead of trying to modify it to get a Hecke eigenform, you basically look at the Hecke orbit of F and then take all the eigenforms in that. So that's what we are doing here. Okay, these are all necessary to construct the cohomology class that we want. If we just take some of them, then we may not get enough cohomology classes. Okay, so this H is the Hecke orbit of my F under This H is not the Hecke orbit. I take the Hecke orbit, I take its image under C, and I look at it modulo pi to the R n plus 1. Okay. So rather than introducing two notations, one for the Hecke orbit and then one for the image is the one that I need, so I introduce the notation for the image. Okay. Then I get a map from the Hecke algebra to endomorphisms of H. So these are E pi mod pi to the R n plus 1 endomorphisms of H. And this is kind of, Hecke algebra is a subspace of endomorphisms of the Hecke orbit of F. And so C is the map that induced, this map phi is induced by C. Okay. And the point of the theorem is to compute what the image of this map is. Okay, the point of the theorem that I started with today is to compute what the image is, and then you show that the image is actually isomorphic to W. Okay, so what you do is you kind of have a W here, and then you go this way, which is by saying how each of the variables pi and epsilon i's act, and then you show that that your map factors through something like this. Okay, so that's why you have to show these relationships that I had on the last slide last time. Okay, that's why I had these kind of relationships. Okay. So that's how the theorem is proved. I mean, there's no point in me going over the proof in detail here, because it's a lot of, it's just kind of verifying that all the relations are satisfied when I go from W to here and then to here, and then showing that it's all well defined. So this kind of thing, and then some dimension computation to show surjection. So it's all very explicit and computational. The proof, you have to do a lot of computations by. Okay, so anyway, I have this map given by the previous theorem. Now, one thing I want to remark about this map is that this map kind of shows that whatever you get is Eisenstein in some sense, right? So this says that these cuspidal eigenforms, modulo pi to the Rn plus 1, they look Eisenstein, because you see what the Hecke eigenvalue is. The Hecke eigenvalue of TL is 1 plus chi epsilon to L. This is precisely what the Hecke eigenvalues of Eisenstein series look like. Okay, this is I mean, for cusp forms, it's hard to describe what the Hecke eigenvalues are explicitly, but for Eisenstein series, we know that the Hecke eigenvalues look like this. So this is saying that even though we are in a cuspidal Hecke algebra, the part that we are looking at actually looks like Eisenstein, and this is precisely because we had this congruence with the modulo pi to the Rn plus 1 with these Eisenstein series that we had. Okay, so this is the important point that we that will be useful in sort of constructing the cohomology class. So we move on to construction of cohomology class. So now up to this point in the proof, it was kind of mostly analytic, right? We looked at cusp forms, and then we looked at all the we looked at sort of constant terms at cusps, and we took some linear combination, and we got a cusp form. So that was kind of the analytic part of the argument, and then the theorem that I just recalled, that was the analytic construction gave that map, this map phi in the theorem. Now we move to the algebraic part of the argument, right? So we have this homomorphism from Hecke algebra. From this, and using Galois representation, we now construct a cohomology class. Okay, so how do we do that? So there's a lot of notation here, because to make it sort of absolutely correct, we can't simply work with this Hecke algebra, or even just its localization, we have to localize it at some prime ideal and then take the completion. So there's going to be a lot of notation, but the essential, I'll try to sort of take you through the essential points of this in spite of all this notation. Okay, so so W was this explicit ring, right? Remember, W was this explicit ring E pi epsilon 1 epsilon r modulo something like this, and then epsilon 1 times epsilon r plus minus 1 to the r L and star chi pi to the r and this kind of thing, right? So it's a very explicit thing, and it's a local ring, more importantly, right? So I have the maximal ideal for that W, which I denote by MW, and I take its quotient, so I get E. Right? This is easy. So I take the whole composition like this, and I take M to be the kernel of this composition. So M is a maximal ideal of the Hecke algebra T. Okay, and you can in fact write it down explicitly. So it's an ideal generated by TL minus 1 minus chi epsilon L and UL minus 1. Okay, so here L does not divide NP, and here L divides NP. Okay, N was the conductor of chi from that we introduced last time. So these kind of ideals, which these are called Eisenstein ideals. So this M is Eisenstein. Okay, because the Hecke eigenvalues look like they are eigenvalues of Eisenstein series. Okay, and I take localization of T at M. So in some sense, I'm not looking at anything which is not Eisenstein. Okay, so this is just like the what happens in complex over complex numbers. So if you the cusp forms are the cuspidal eigenforms are parametrized by sort of maps from Hecke algebra into something, right? Hecke algebra into C, and so so this is the same thing happens for lambda-adic things, and I'm killing off all those other cusp forms which are not Eisenstein. So this is a standard thing that one does. So I'm killing off everything which is not Eisenstein. So and I take the total ring of fractions of my localization. It is product of some fields. Okay, this is product of some fields. And in fact, what are these HIs? These are actually cuspidal eigenforms in this H. So these are all the eigenforms with the following property. But before writing down this, before sort of going over this property, let me say that one important point is that the ring T sub M, it injects into L. And the reason for this, I mean, you know, when does a ring inject into its total ring of fractions? When it's reduced, when it has no nilpotent. And this Hecke algebra has no nilpotent. And the reason for this is there are no old forms. So there are no old forms. So all the forms here have sort of tame level M. There are no old forms, and that's why this is reduced. So this is kind of minor but important point that TM injects into this. So this each of this field in this product is a finite extension of the total field of the quotient field of lambda. Lambda is a domain. Remember, if I take lambda sub hi to be the integral closure of lambda sub 1 in this. And MHI denote the maximal ideal above T, then these Fourier coefficients have this property just by construction. So you just have to unravel all the definitions and you will see that these these two things are satisfied. And in fact, not only that, these are all the forms which satisfy these properties. There are no more forms, lambdatic forms of this particular level, which satisfy these properties. So these are all the lambdatic aspidal eigen forms of level n which satisfy this property. Okay, so so from this F that we constructed, we get all the yeah, I mean, well, the definition of L sub HI is just something that appears in this product. So there is no way to describe this more explicitly in some sense. Like we can't. So there is a question saying, can you give more details on the definition of the fields L sub HI? So we can't really construct these things explicitly. This is the whole. I mean, this is kind of the problem that we can't describe these more explicitly than this. We can only construct this F, and then we can look at. Then we just kind of say, okay, I want to consider all the eigenforms in the Hecke orbit of F, and this is a way to do it. So you take this, and then whatever appears in this product is what it is. So. So there's no, yeah, I don't know if that answers the question. Yeah, this is how this LHI is defined, and that's it. Yeah. Okay. All right. Great. So these are all the forms which are Eisenstein, right? But now the good thing is, I mean, even though we have obtained them abstractly, we do have these are eigenforms, and so there's a there are Galois representations attached to these. So so this is very much like the Galois representations that attach to ordinary forms that Shonak mentioned in his talks, but this is over totally real fields. Okay. So these were constructed by Wiles in some special cases first, and then Hida, and so I'll attribute this to Hida Wiles. So there exists a continuous irreducible representation rho I from GF to GL2 of these fields. Okay, so kind of one important point here is these are not these are in fields, not inside lambda HI. Okay, I mean, because GF is compact, you can always choose a lattice so that you can always choose a isomorphic representation which takes values in lambda HI. Yeah, but that depends on some choices. So priori these are in HI, L of HI. But what are the properties? So I'll write down some important properties of this. So as in Shonak's talk, these are unramified outside the level and outside P. Okay, so everything in the level it may be ramified, and at P it is definitely ramified because as Shonak said, determinant is the p-adic cyclotomic character. So in this case, it is this epsilon. So epsilon times something. So it's unramified outside NP. Well, outside NP, if it's unramified, you can talk about what its value at Frobenius is. And so it's some 2 by 2 matrix, and you can ask what its characteristic polynomial is, because even, I mean, like rho of Frob L is kind of not such a well-defined thing. It depends on sort of how you choose this thing, but characteristic polynomial is a more canonical thing. So the characteristic polynomial is given explicitly by this. So x squared minus the coefficient of the linear term is the Hecke eigenvalue of the operator TL. Okay, so this is if you have normalized your thing, then this is Hecke eigenvalue of TL if it's normalized. Okay, and then the determinant is just chi times epsilon. So as okay, so that's what happens at good places. good in the sense of unramified places. What happens above P? At P, primes above P, something interesting happens. So these are ordinary forms because we had hit them all by this Hida's idempotent operator. So when you restrict your row to GP, you get something. You get a reducible representation. Okay, so it's isomorphic to something which explicitly looks like this. It's upper triangular with the top entry chi times epsilon times some eta sub p. Okay, eta sub p is some unramified character. And if you have an unramified character of the Galois group, you just have to specify what it does to uniformizer, if using local class field theory. So because on units, it's trivial. That's what it means to be unramified. So at a uniformizer, it gives you this Hecke eigenvalue of UP. So right? So this is the kind of thing that happens. So it's upper triangular with chi times epsilon times eta, some unknown quantity here, 0 in here, and then eta again here. So eta inverse and eta. Okay. So this is the quantity that will give us our cohomology class, as we'll see. But you can sort of already see that this is an extension of depending on, this is an extension of this by this. So it's kind of, this is the thing that's giving you the extension. So this star better be something non-trivial. Okay, so all right, so that's the Galois representation. Now, how do we actually get our cohomology class? Right. So some details now. Now, locally at each P, our Galois representation is a reducible thing, like upper triangular thing. So there's a natural choice of basis at each place P. Okay, and then we can make a choice of basis globally, right, on GF. Now we have to do it in some non-compatible way, because we don't want our global representation to be reducible in any sense. That, I mean, it is kind of, I mean, even modulo something. So we have to make a choice in something like non-compatible way, and this is what Maser calls Ribet's wrench. Which is kind of these non-compatible way of choosing global basis for our representation and then local basis. So you will see this explicitly how it's done now. So I'll not say much about the words here, but I'll just sort of tell you what we do. Okay, so for each I and each P, we denote by V sub P comma I the eigenvector for rho sub I. So this is a reducible but not decomposable thing, and so there's only one eigenvector for each of those locally, and so we fix that I mean up to scaling. So we fix an eigenvector like that. And the reason for this is the next lemma. So the next lemma, you have to show that there exists an element in GF for which chi of tau is not 1. Okay, something non-trivial. Chi of tau is not 1. And Vp is not an V sub P comma I is not an eigenvector for rho sub I tau for every I and for every P. Okay, and this is just something you know like it's kind of like a Shepard density that you can choose it for you can choose it for one I and P, and then amongst those you can choose another one, and so on. So it's some kind of topological argument that such a thing exists. So it's not hard. It's proven in our paper, for instance. So in Ribets and Wiles, you just need this condition. You kind of don't need this condition. So if you just need this condition, then it's very easy. You can choose something like complex conjugation. Tau is complex conjugation, and then chi of tau will be -1. So there it's kind of easy, but we need this extra condition, as you will see later on why. Now I'll tell you what it implies exactly. But let's say that we can choose such a tau. And then because I want to find eigenvalues using some limiting process, I have to take lambda-adic completion of my T sub bracket M. So I'll call this by T sub M. And then the total ring of fractions will be L sub M. So this is just putting together all the rho i's. This is kind of putting together all rho i's. We get this. So this is a product of yeah, this is product of all the I mean that this contains this, right? And then this is some kind of completion of that. Okay, so you take completion of each of this and then take the product, and that gives you this. All right, so this is just putting everything together. So this is still due to Hida and Weil's existence of such a representation. So there exists rho from GF to GL to M, and now I can write it somewhat more canonically. So rho is unramified outside NP, and the characteristic polynomial is exactly this one. So what is this TL bar? TL bar is image of TL inside this L sub M. Okay. So because we are considering all of them together, this is the way to write it. And rho restricted to G P for any P dividing P is upper triangular like this. Okay, is isomorphic to something upper triangular with this eta P unramified. And what does it do at a uniformizer? It sends it to UP bar, image of UP inside this this LM. Okay, so this is just putting together all those things at once. Yeah. Okay. So now we can fix a basis. This is rho tau. This is tau, not T. This tau. So we had this tau from the previous lemma. Oh, it says, can you give the definition of an unramified character? I mean, unramified character just means that it is, if you look at it on the Galois side, like a character from Galois group into Q bar cross or something, then unramified just means that it's trivial on the inertia subgroup. So unramified at V means it's trivial on the inertia subgroup at V. If you look at it on the sort of adelic side in local class field theory, then it just means that it's a character on FV star, and then it's just trivial on the units in the ring of in the integer ring of FV. Okay, on the Galois side, it's simply trivial on the inertia subgroup. Okay, so that's why there is this. I mean, I'm looking at this as a Galois character, so that's why there is this. There is this reciprocity. So I'm using local Artin reciprocity map. So this is something that yeah, reciprocity applied to the uniformizer. Reciprocity applied to units will give me inertia subgroup. So it's trivial on that. Okay. So now I can fix a basis so that rho tau is diagonal. Okay, so this one can do. This is all characteristic 0, so there's no subtlety happening. I mean, I'm doing it over ease also. So this is fine. Moreover, because yes, I can find lambda 1 and lambda 2 like this, and I'll have this congruences. Okay, lambda 1 is congruent to 1 mod m, and lambda 2 is congruent to chi of tau mod m. And how does this come about? Because I know what the characteristic polynomial is. So this epsilon is 1 modulo m. So that's why the epsilon doesn't appear. Okay. All right. So yeah. So that's why the like lambda 1 plus lambda 2. I mean, maybe I'll write this here. So TL is kind of 1 plus chi epsilon L, and then lambda 1 plus lambda 2 is 1 plus chi epsilon L. Yeah, it's not exactly that. That's why I'll write tilde here. And then lambda 1, lambda 2 will be chi epsilon, this kind of thing. Okay. And so using this property, you can get that lambda 1 is congruent to 1 mod m, and lambda 2 is congruent to chi epsilon of tau mod m, but epsilon tau is just 1 mod m. Okay, so now we have fixed a basis. Now we have rigidified our global Galois representation, right? So we can write down matrix for each row sigma. So for any sigma in the Galois group, I write it as A sigma, B sigma, C sigma, and D sigma. And this is an element of GL2 of LM, and all these things will play some role. B is the most important one, right? So this B sigmas, these are the things that will give us our chromology class. Okay. Now, I mean, strictly speaking, I kind of have to do this kind of argument before saying all this, this kind of thing. But this is just the easier way to present it. So what happens is, that like what is rho of Frob L, we know what that looks like. At least we know what its trace looks like and what its determinant looks like. And trace of rho Frob L is the image of this Hecke operator TL, and determinant of rho Frob L is this chi epsilon times L. And if you know something at Frobeniae of sufficiently many primes, then you know it everywhere by Chebyshев density, right? So Chebyshев density will tell you that trace is 1 plus chi sigma, right? This is exactly what I was writing here. And then determinant will be chi sigma. Okay, so I don't need it immediately, so I'll not write it down. So these A, B, C, and D, they a priori live only in LM, right? They don't. They are in the field total ring of fractions of my TM. Okay, I don't know whether they live in TM or not, and this is kind of slightly tricky whether they do or do not. And we'll soon show that actually, because of the way we chose our tau, they A and D live in TM. We don't know anything about B and C. Okay, and B and C most probably don't live in TM. But what we do know, just from this Chebyshев density argument, is that A plus D lives in TM, and in fact it's congruent to 1 plus chi mod this. Okay, so this already kind of tells you that this lives in TM. So this is in TM because this is this is like TL. Okay, so when sigma is Frob L, this is TL. So for each Frobenius, it lives in TM. So by Chebyshев density, it lives in TM. But now we are going to show that A and D also live in TM. This is the argument. So maybe I'll just make one small remark here, which is maybe just a technical remark for some experts who may be in the audience. So we have some integral generalization of this Gross-Stark. Shamit and I have done this. So this and in this integral generalization, we stay away from prime 2. Okay, in this Gross-Stark, we don't need to stay away from prime 2. But this is the technical point, that we don't know how to show A and D are inside Tm by this argument that I'm going to give now. If I want integral refinement at 2, then I don't know how to show this. This is because what is called like residually this representation is indistinguishable mod 2. So I don't, these lambda 1 and lambda 2 are sort of, they'll be congruent modulo 2. And so I can't do this argument. And most probably these A and Ds will not be in Tm for any good choice of basis. So that's why the question is sort of very hard at p equal to 2. And I believe it requires some non-trivial new idea at p equal to 2. Okay, but here we are working in characteristic 0, so we don't care much about whether p is odd or not. All right, so I know that A sigma plus D sigma is 1 plus chi sigma modulo m. I can now write the same thing with sigma replaced by sigma times tau. So sigma times tau gives you A sigma tau plus D sigma tau. This is congruent to 1 plus chi sigma times chi tau, right? But I can find out what A sigma and D sigma is in terms of A sigma tau and D sigma tau. This is simply because rho is a representation. So rho of sigma tau is rho of sigma times rho of tau. I write it as a matrix, I get this. So in short, I get something like this. Okay. And putting together all these congruences, you can deduce this. Okay. And here we kind of use that chi of tau is not 1. Yeah. So lambda 2 is not 1 modulo. All right. So we get that these two are also in Tm and they are congruent to. I mean, you can't talk about congruence modulo m if you're not in Tm. Right? You can't talk about congruences if you're not in that integral ring. Oops. So these are also in Tm. Okay, so this is the argument to show that A and D are in Tm. Okay, now so those were A and D, and now B, as I said, plays an important role. So let's study what happens to B. So for two elements in GF, this should be GF. For two elements in GF, I know that rho of sigma sigma prime is rho of sigma times rho of sigma prime. And I just write this down in terms of matrices and sorry about that. And compare the upper right hand term. So I compare this and the upper right hand term of the product. So what is this? B sigma sigma prime is A sigma times B sigma prime plus D sigma prime times B sigma. Now, if I look at it modulo m, I know that A sigma is 1 mod m, and I know that D sigma prime is chi of sigma prime mod m. So what I get is B sigma sigma prime is B sigma plus chi of sigma prime times B sigma. So this looks like a co-cycle relation. Okay. So actually the co-cycle that I actually take is this. So kappa of sigma is chi of sigma inverse times B sigma. Right. Sorry, this shouldn't be, this is not a comma. Yeah, that was supposed to be a dot. Anyway, so B sigma, so if I take this, then it is actually a co-cycle with values in B bar times chi inverse. So I'll say what B bar is. And I can take its class in the cohomology. So I get a cohomology, Galois cohomology class. So what is this B sigma? What is this B, this module B? This is just a TM module generated by all the values of all these upper right hand entries. Okay, so I take all these upper right hand entries and I take the TM module generated by them. So as I said, this upper right hand corner star was the one that's going to give me my cohomology class, and this is what's happening. So I take all the values that it generates, and then I get this this explicit cohomology class. So because to get the co-cycle relation, I had to go mod M, and so this is what I have to do. Sorry, my M hat is just extension of M to T sub M. So here I'm not. Yeah, here I should also write M hat. So I guess. Anyway, I'll not be very precise with these hats or no hats. Anyway, so that's how I get the cohomology class. So we have constructed the cohomology class that we want. Now we have to use it to show Gross-Stark conjecture. So at this point, let me say that I mean, modulo some technical details and sort of certain difficulties. The proof up to here is kind of very is not. I mean, this theorem about the Hecke algebra homomorphism, that's a new thing. But apart from that, whatever has happened up to here is very similar to what happens in Dasgupta, Dharma, and Pollock's paper. That homomorphism is the first kind of non-trivial new thing in this paper, and then whatever happens from now on is the non-trivial new thing in my work with Dasgupta and Ventulo. Okay, so up to this point, kind of it's very similar. So you have this this kappa that Dasgupta, Dharma, and Pollock also had. And from this kappa, they just constructed a cyclotomic class. Remember, they are in R equal to 1 situation. So in that situation, they just construct a cyclotomic class and the cyclotomic class has to take values in E times, I mean, E chi inverse, right? So they just take a map from B bar to E, which is just given by going modulo the yeah, I mean, there's a sort of canonical map like that, and then you just show that class is actually a cyclotomic class. But as I said, we don't know how to show that when R is bigger than 1. We don't know how to construct R distinct, linearly independent cyclotomic classes. I mean, we don't even know how to construct one cyclotomic class, let alone R. Anyway, so that's just a comment. So from whatever happens from now on is different than the Dasgupta Dharma Pollock paper. So firstly, we look at the behavior of kappa locally. So kappa is a sorry. Could you explain how to use your choice of tau to make vector a non-eigenvector? Oh no, I did not explain at all. I mean, this is just this lemma that you can choose a tau so that none of these where did it go? None of these VPIs are eigenvectors for rho I of tau. So I did not explain how to prove this. So I mean, we can just look at the paper. It's not difficult. It's just some topological argument that you can make such a. I mean, you know, like for you, if you take all the taus for which this is an eigenvector, then it will be some kind of a subgroup of G tau, and you can show that of infinite index, and then you can show that how did I use it to get a co-cycle? Well, I mean, up to this point, it's not played much of a part actually. So this co-cycle you will always get. I have said nothing about the co-cycle, right? I mean, up to this, I just said we have a co-cycle. Now, this co-cycle could be 0 for all we know. Okay. But the fact that it gives something non-trivial is what is going to come next, and that's where we'll use our tau. No, so for the construction of co-cycle, we don't use this kind of tau yet. But if we don't choose the tau carefully, we might just end up with 0. Yeah, thanks. Yes, that's a good point. So tau will be used now. So I'll say where it's used. Okay, so we study local behavior of kappa. And so there's this, as I said, locally, there's a basis which makes the representation upper triangular. And globally, we have fixed a basis with this, which diagonalizes this row of tau. And so we have then we have change of basis matrix, right? We have two distinct bases, so we just have the change of basis matrix, and I call this ABCD, okay, AI, BI, CI, and DI for each prime I, each prime PI, and again then I compare the upper right hand corner of these two sides. So I get A times times A sigma times AI plus B sigma times which one? Yeah, which one am I? No, yeah, I'm comparing the upper left hand corner this time. Okay, I'm comparing the upper left hand corner. So I get A sigma times AI plus B sigma times CI is equal to A sigma times this chi epsilon eta I inverse. And if you rearrange that, this is the relation you get. B sigma is AI divided by CI times this. Okay. So here is where we use our choice of tau. So if we did not choose tau carefully, we could end up with AI and CI equal to 0, or one of them, AI or CI being 0. So our choice of tau implies that AI is not 0, and I mean, it kind of is maybe a, yeah, sorry, let me write it in a more, I mean, these are elements of a product of some field. So AI, CI, these are in LM, are non-zero divisors. It's not enough that they are non-zero, they are not zero divisors is what we need. So first of all, I can invert it. Right? They are units in LM. And so this is the relation I get. So this is how our choice of tau is used to show something is non-trivial now. Okay, so here's a lemma, which I'll just orally say how one gets it. So we have to show that it's unramified outside primes in R1. Okay, and at primes in R1, it is definitely ramified. Is just a comment I would make. Now, there are two kinds of primes outside R1, or maybe three kinds. So one are sort of good primes away from N and P. And then there are primes which divide NP but are not in R1. Okay. So if you are away from P, the characteristic, then you can easily imagine that a p-adic representation will be unramified away from P. That's kind of not very hard to imagine, because the ramification will anyway be some finite thing, and these are all characteristic 0 thing, right? They are taking values in some E vector space. So this is an E vector space, in fact. This is an E vector space. So they are all taking values in some E vector space, so you can't have a finite amount of ramification. So away from P, so away from P meaning I have to, I mean, I want to show that this is unramified at primes which are not above P. Away from P meaning I'm considering primes which are not above P. So I have to show that rho restricted to sort of IV is trivial for all V which are not in R1. And so I'm just saying that if V is not above P, then you can easily imagine that this representation is unramified. So and you can easily check that actually it is. You just need to use inflation restriction sequence. So the tricky thing is what happens to primes which are in R, right? So these are above P, but chi of that prime is not 1. And in this case, what happens is that this turns out to be a unit. So I'll not write this, but I'll just say, so when you are inside, when you are in R, when you are in R but not in R1, so frob of chi is chi of frob V is not 1. So this kind of thing is a unit. So in fact, what it shows is that AI by CI is inside inside B, because if this is a unit and B is the module generated by all the B sigmas, so this lies inside B. And so that's how you can actually show that that kappa is in fact not just unramified, it's locally trivial. It's locally it's not just trivial when restricted to the inertia subgroup. It's trivial when you even restrict it to the decomposition subgroup. Okay, so that's what happened. And then at R1, we are not, this lemma is not saying anything. And in fact, at R1, this will be genuinely ramified, because you can show that there are no classes in here which are unramified everywhere. So it has to be ramified at least some places in R1, and in fact, it is ramified at all places in R1. And then there's some second technical lemma that I'll not again not prove and not even say much about what the idea is. But this is kind of an important ingredient in the proof. You see, we don't have much control about which elements are integral and which elements are not. We are working in the ring of fractions of Tm, and most of our things are not in Tm but only in Lm, and we don't have much control, and that's why I kind of emphasize the thing that A and D we can show are in Tm. So that's one thing we can show. So these are kind of, all these capital AIs and capital CIs and the module B and the quantity B sigma, small b sigma. These are just elements of LM. And, we have no idea how bad the denominators are. We have no idea what the structure of B is like. We have no idea how they kind of, if you multiply capital AI by small b sigma, whether we get something integral or not. So these are kind of, we don't have much control over these things. So that's why this kind of thing is a nice, is a very nice statement. I'm just trying to say why this statement you would think is useful. Now, these are all in TIs, and this is saying that actually, even though BI was this huge module generated by all the upper right-hand corner entries, its non-integral behavior is just determined by these AI by CIs. Okay, so that's why this is a very nice statement, that its denominators are just determined by what AIs and CIs are. And this will turn out to be useful, though I'm not sure I wrote down that step. So let's go on. Now we want to compute the regulator. Okay, so this is the final stretch. So recall that we have fixed a basis of this E tensored with U chi. And then recall that Pothutate gives us this, Pothutate duality gives us this orthogonality between kappa and U's. Okay, so we have this. Now U, well, here's some technical point. So this is some technical point. This U is an E tensored U. So I should ideally write it like, as some kind of tensor thing. But I'll just pretend for simplicity of writing it down that all these U's are in capital U. Okay. because otherwise it is just notationally much more complicated. But that's how, I mean, this complicated thing is done in the paper, so you can look at that. All right. So restriction of kappa at the pith prime, and then you evaluate it at uj. This is same as b bar evaluated. I mean, b bar evaluated at sigma ij. So what is sigma ij? Sigma ij is you apply the ith reciprocity, reciprocity, local Artin reciprocity map at p sub I to uj. So that's my notation for sigma ij. I don't want to write uj here because it is not independent of I. It really depends on I. So that's why I introduced this new notation. Otherwise, as you have seen in the lectures, I try to avoid introducing new notation. But sometimes it's kind of inevitable. So, okay. And then we have this relation that B of sigma is A by C times this quantity. Now there is no chi here. And the reason is that chi is identity on the decomposition group at all these PIs. So chi kind of disappears from here. Then how you know what eta does to a uniformizer? It sends it to UP. So if I have some other unit, so you can just think of the sigma ij as a unit. If I have some other unit, what will eta I send it to? You just have when I say unit, I mean it's a p unit, right? This is OH1 over P star. So it's not like unit in the sense of global unit. It's a P. It's just an element of H sub F sub Pi. So if you have some other element of F sub Pi, what will it send to? It will send it to U to the power odd of that element, right? Because eta is trivial at all the units. So you write your element as a unit times your chosen uniformizer to some power, and then eta will send it to that particular power of UPI. So this is why you have this, right? And then I can modulo modulo some, yeah, what was I is this kernel of phi. So modulo this thing, I can write it like this. This is just like approximating, this with this. Okay, but this is yeah, just unraveling the definitions again. And then the lambda-adic cyclotomic character. This is more or less by definition, it's 1 plus log applied to that element times pi plus to some power, but modulo pi square, it is just 1 plus log times pi. Okay, so this is again by definition of what the lambda-adic cyclotomic character does. I mean, these things are not often explicitly written down in most places, so you have to work them out. But this is not easy. I mean, this is not hard. This is just unraveling the definition. So even if you kind of are getting lost in this, you just have to think about it a little bit. And then A applied to this, which kind of appears here, I just write it like this, 1 plus this modulo. Okay, so remember that A is congruent to 1 modulo M. So modulo M, it's 1, but modulo M square, it may be something different. So this A prime actually lies inside M. Okay, that's why I can write it like this. And so I rewrite my B sigma. I let the bar go, so I'm not looking at it mod M anymore. So my B sigma is A by C plus these quantities, all these things that appeared here. Okay, so this one and this one cancels, plus something in M squared. So because I'm not working, I mean, because my M is just some random thing in M squared, I can modify that to write B and not B sigma, B bar anymore. Okay. Now, going back to our orthogonality relation here, we get that if we sum over all these i's, these quantity, we get 0. And so we get that all, if we sum all this over I, we get 0. Okay. But now if you look at this R by R matrix, there are two indices here, I and J. So we can look at an R by R matrix indexed by these I and J's with these entries. Okay, just these entries. Now, yeah, so depending on how you have arranged it, let's say sum of the entries in the rows is 0. And so that's why the determinant is 0. Right? If we take this R by R matrix, its determinant will be 0, because when you are summing all the entries in all the rows, you get 0. Right? So the rows are linearly dependent. Okay. And so here's sort of what I wrote earlier, that these are not 0 divisors, right? So these are in L, M, cross. And so I can so now if you observe this formula, everything is integral except these AIs by CIs. Okay. Yeah, everything is integral except these AIs by CIs. And actually here is the point where I have to use that B is contained in this summation AI CI times M, because when I go from B bar to B, I have to be able to change this thing by M and still get something integral. So here that lemma is used, and I should have written it more carefully. So here, sorry, I am already 2 minutes over, but let me take a couple of minutes. I'm almost done. So here's that lemma: B contained in summation AI by CI times M is used. Okay. All right. So so I can cancel these AI by CIs, and whatever remains, this still has determinant 0. But now everything is integral, so I can apply my phi map to it. Right? Phi is only defined on TM. Not outside that, not on LM. So I apply phi to it. This UP minus 1 goes to epsilon I, this goes to this, or the MJs kind of land inside MW squared. And there's a relationship in my ring W. And what is that relationship? So pi times epsilon I is 0 inside W. Right? So that's why the determinant of this matrix, it decomposes as sum of two determinants. So this is not something that usually happens, right? So that's why the determinant, it decomposes as sum of two different determinants. And you just, determinant of this diagonal matrix with epsilon i's. So there's another relation here. Product of all the epsilon i's was this thing. Minus of that minus 1 to the R times ln and so on. So you just write this, and then there are two cases. So remember, we are always in case 1. In case 2, things are much more complicated, and so I did not touch upon them. But now if the first conjecture of Gross fails, then we know that this is 0 modulo pi to the R plus 1. So this thing is 0. And so we get that determinant of LIUJ is 0. So we get that this is 0, which implies that the regulator is 0. Right? I said that if Gross's conjecture fails, then we have to show that 0 is 0. So that's what we show here. But if the first conjecture is true, then Rn is same as R, and we get what we want. Right? So that's how it's done. Okay. So sorry about going 5 minutes over.
Thanks, Mahesh, for the wonderful talk. Are there any questions?
Can I ask a question?
Sure.
So, I mean, it's kind of related to your second talk, but what you also said, like about this gross conjecture, this R analytic itself is equal to R, and you said so. It follows from like Chanel's conjecture, and so is the only method. Then you said like So transcendental methods are the only methods, and with
No,
which
no,
this can be attacked.
no, that's probably. I mean, how do you? It's an unsolved thing. So how do you know whether these are the only methods? That is my suspicion that transcendental methods are the most promising way into it. But as you know, with Leopold, there have been many claimed attempts for Leopold, and most of these things were not transcendental, or all of them. I mean, that I know of were not transcendental methods in some sense. So yeah, it's similar for Gross-Kuzmin as well. Like people have tried approaches not using transcendental theory. But I think it's like on the algebraic side, it all seems consistent in the sense that we don't have to assume Gross-Kuzmin to prove our result. If it fails, then we just show 0 equal to 0. It's the same with Wiles. Like Wiles doesn't have to assume Gross-Kuzmin. If the order of vanishing of the L function is higher, he just constructs more extensions and shows that the two sides are equal, like the order of 0 of the p-adic L function and the order of 0 of characteristic element. They are equal. And then the same with Leopold. Like he just shows that if Leopold fails, then main conjecture predicts existence of some extension, and he can construct them. So in that sense, like it all seems these two conjectures seem to lie outside at least class field theory and maybe some extensions of it. So I would be very surprised if it kind of just follows from class field theory, or even just a slight extension of that. Yeah, is there a nice like the number of linearly independent? Yeah. So there is, in fact. So I think I mentioned this the other day. If you take the cyclotomic ZP extension of H being this field cut out by chi, and you look at the maximal abelian P extension of H cyclotomic, in which all primes above P split, then that is a finite extension of H cyclotomic. So that's a consequence of this Gross-Kuzmin conjecture, Gross's conjecture. Yeah. So there are these, because it's saying something about order of vanishing of the characteristic element, characteristic ideal. So yeah, it is.
Any other questions or comments? If not, let's thank Mahesh for a wonderful lecture series.